In physics, we use meters whenever we talk about distances. That makes it so that the units will cancel out when we need to, and it basically works together. Unfortunately, when we're talking about waves, we don't always have the luxury of being given just plain meters. So the first thing you need to do is see what we have here. We have a light wave as a wavelength of 490 nanometers and a speed of 3.0 times 10 to the 8th meters per second. What is the frequency of the wave? So this right here might throw you off. This is a quick Google search to find out what this means. Typically when we're talking frequency, you'll see words like kilo or mega or giga when we're talking about hertz. So we'll see kilohertz or megahertz or gigahertz or anything else like that. And basically kilo is 1,000 hertz, so we could represent that with a 10 to the third. Mega is 1,000,000 hertz, which would be 10 to the sixth. And giga would be a billion, which is 10 to the ninth. So if we remember that, that's going to help us with our problems. And like I said, if you're unsure, just Google it. When we're talking wavelengths, a lot of times we're going to see stuff like the nano. So on the other end of the spectrum, we'll see our nano is going to be 10 to the negative 9. And our nanometers up there would look like this if we were to write it out. Sometimes we'll see micro, which is 10 to the negative 6th. And that's a fun unit to write, micrometers. And there are others. So like I said, if you're unsure, just look it up. So let me separate that from the problem because this is just sort of informational. Now back to our problem, we can write that the wavelength is 490 nm because as I said, we looked it up if we weren't sure. But we need it in meters. So that becomes 490 times 10 to the, and just because we're not sure, we would check maybe, times 10 to the negative 9th meters. Technically, that's not correct, so we will have to move this decimal point over to become 4.9 times 10 to the negative 7 meters. Also given is our speed. So we know V is equal to 3.0 times 10 to the 8th meters per second. And it is asking for the frequency, which is our unknown. Now, because we have these three variables, we will just use our standard wave equation. Velocity is frequency times wavelength. We will put our numbers in, substitute. And so velocity is 3.0 times 10 to the 8th meters per second. And it's worth pointing out at this time that regardless of the numbers, if that intimidates you, it doesn't matter at this point. We were able to pick out what is the wavelength, what is the velocity, and that frequency is our unknown. We have set up our equation not based on the numbers, but on what they are. So now we do have to deal with these numbers, but at least we can set them up correctly. Frequencies are unknown. Multiply that by 4.9 times 10 to the negative 7th meters. Okay, so now we can start to solve this. And we need to get this frequency by itself. So we divide both sides by 4.9 times 10 to the negative 7th meters. Anything over here. Whatever you do to one side, you have to do to the other. Okay, so this all cancels out, so that frequency is all by itself. The meters here cancels out with the meters up here. And now when we go to solve this, we do have to deal with the numbers, but just like before, we take this base number and divide it by this base number here because it's a division problem. So when we do that, we end up with frequency is equal to, and 3.0 divided by 4.9 is going to be 0.61. So now we have our exponents times 10 to the 8th divided by times 10 to the 7th, and whenever you're dividing exponents, you subtract. So 8 minus a negative 7 gives us times 10 to the positive 15. And we're left with per seconds, which is hertz. Now, of course, that is not complete because it's not properly set up. So we have to move our decimal point over 1. And we find that frequency is 6.1 times 10 to the 14 hertz. We put a box around it and call it done.